Our next example is using characteristic polynomial. For using the characteristic polynomial approach for the solution, the first thing is that you need to assume that n is equal to 3 raised to power k. Why 3 raised to power k? Because we are dividing over 3, so it should be 3 raised to power k. If we are dividing by 5, then it will be 5 raised to power k. The first value of k should be 0. Why 0? Because the first value of n is 1, and how to make 3 raised to power k equal to 1? By raising 3 to the power 0. So the next one will be 1, next one will be 2, 3, and etc. So we assume that n is a power of 3. Substitute, we will get t 3 raised to power k equal to t 3 raised to power k over 3 plus 3 raised to power k plus 2. And this is equal to t 3 raised to power k minus 1 plus 3k plus 2. By rewrite, we will have t 3 raised to power k minus t 3 raised to power k minus 1 equal to 3k plus 2. For the homogeneous and non-homogeneous recurrence relations, we were familiar with the name of the recurrence relation by A, and the subscript were linear. So n minus 1, n minus 2. So we were depending on the subscript. For this recurrence relation, the last one, we can assume that k as a superscript is similar to k or n as subscript in homogeneous and non-homogeneous recurrence relation. So like for example, what I mean by here, probably you can assume that this is ak and this is ak minus 1 in homogeneous and non-homogeneous recurrence relations. In this case, this recurrence relation that we are obtaining is non-homogeneous because some of the terms do not have t 3 raised to power k. This part will be the homogeneous part, and this part is the function, but here it's not going to be in terms of n, it's going to be in terms of k. So next is finding the characteristic polynomial. So the characteristic polynomial. And the characteristic polynomial is equal to, for the homogeneous, it will be x minus 1. Why minus 1? Because there is no number in front of t 3 raised to power k minus 1. And for the function on the right hand side, I will use different color. Since we have exponential, so for the exponential we will have x minus 3 plus constant. For the constant is x minus 1, and this is equal to 0. The general series, so we have, how many roots do we have? The first root is equal to 1. The second root is equal to 3. The third root is equal to 1. So 1 is repeated. Put this thing in your mind. Step number 3, the general solution. The general solution. So the general solution is t 3 raised to power k. It is not tn, because we found the characteristic polynomial for this recurrence relation after we transformed it into a different form. So this is going to be equal to, the first, for the homogeneous, we will have c1 multiplied by 1 raised to power n plus, now for x minus 1, it is already repeated. So since it is repeated, then we will assume that it is combined with x minus 1. So what we will have? We will have a k plus b multiplied by 3 raised to power k. So since 1 is repeated, So we assume that we have C1 plus C2 multiplied by K. But I'm replacing C2 by A, as you remember that for the constants for the particular solution, we want to use different letters than the homogeneous constants. So we have now two parts of the recurrence relation. Here the solution, the general solution. This part obtained from the homogeneous and this part obtained from the non-homogeneous. So we will call this one T H 3 raised to power K, and we will call this one TP 3 raised to power K. Now when we say Tn and TH, TH stands for homogeneous and P stands for particular solution. Now finding the constants. Like what we have done before, I will show you how to find the two constants using two methods, one from boundary conditions, the other method by using the particular solution. So this is the particular solution TP and homogeneous recurrence relation. So method one, finding the constants from boundary conditions. For the boundary conditions, we have only one value, which is the initial value. Let us find two more because we have three constants. And remember that for the recurrence relation we are dealing with, it is in terms of K. So K, if it's equal to 0, then we will have T 3 raised to power 0, which is T1, and T1 is already given as 1. For K is equal to 1, then we will have T3 raised to power 1, which is T3, but T3 can be found from the original recurrence relation, which is equal to T1 plus 3 plus 2, which is equal to 6. How did we find this value? Because when you substitute K equal to 1, you are looking for T 3 raised to power 1, and 3 raised to power 1 is in fact T3. So you go up to the original recurrence relation, which is this one. If n is 3, then you will have a 3 over 3, which is 1. So it will be T1 plus 3 plus 2. And this is how we found those values from the original recurrence relation. Now for the next value, because we need 3 values, it will be T 3 raised to power 2, which is equal to T9. And for T9, it's equal to T3 plus 9 plus 2, which is equal to 17. Because T3 is 6, 6 plus 9 is 15, plus 2 is 17. So we found 3 values. Now we need to find a system of equations. So K is equal to 0. We will have C1. Let us see the recurrence relation. Since K is equal to 0, so we will have C1 plus 0 plus B is equal to 1. Now for K is equal to 1, again we need to see the equation so that we can find the answer. So K in here is equal to 1. K is equal to 1. So what we will have? We will have C1 plus A plus 3B is equal to 6. And last, when K is equal to 2, we will have C1 plus 2A plus 9B is equal to 17. So we have three equations. By using your calculator, solving for the constants, we have C1 is equal to minus half, A is equal to 2, and B is equal to 3 over 2. So when we substitute, we will get T 3 raised to power K is equal to minus half plus 2K plus 3 over 2 K times 3 raised to power K. We will leave this equation up to here without substituting for K in terms of N. First, we need to show you method 2 how to find those constants for using method 2, because we will end up with the same equation, and then we will show you how to write this expression in terms of N. Now method 2, we will find the constants into two steps. One, find A and B from the particular solution, which is Tp 3 raised to power K. Let us write our recurrence relation first. And what is Tp? And this is, so let me write it here. This is equal to AK plus B times 3 raised to power K. So when you need to substitute, into this equation. You have T 3K minus T 3K minus 1 is equal to 3K plus 2. For each occurrence of T, you need to replace it by this equation. So for T3 raised to power K, we will substitute by this. Let's do the substitution. So for the first one, for the first T, we will have A, K plus B times 3 raised to power K minus. Now for T3K minus 1, if you look at this equation, what changes will be on the right hand side when this one is K minus 1? Here will be K minus 1, and here will be also K minus 1. So the answer will be A multiplied by K minus 1 plus B times 3 raised to power K minus 1, and this is equal to 3K plus 2. Let us continue on the next page. Do the simplification. So this will be equal to AK plus B times 3K minus AK. Here I will multiply minus to both terms, plus A minus 1 over 3 B times 3K is equal to 3K plus 2. So how did we get minus 1 over 3 B times 3K? Look here, if you take a 3 to the power K, because we have a 3 raised to power K, we have 3 raised to power K. If you take 3 to the power K common between in here, so you will end up with a 3 raised to power minus 1, which is 1 over 3. And you have minus, so it will be minus 1 over 3 multiplied by B by K. Rearrange the equations on the left hand side and make it all those with the 3 raised to power K on one side, and the others will be on the other side. So we will have 3 raised to power K B minus 1 over 3 B plus, and notice here that minus K will go with K, so plus A is equal to 3 raised to power K plus 2. Now do the matching. From here you can see that A is equal to 2, so you match this value with this value, and you match this term with this term. And also b minus 1 over 3 b is equal to 1. So we will have 2 over 3 b is equal to 1. So b is equal to 3 over 2. So the recurrence relation at that step is equal to C1 plus 2k plus 3 over 2 times 3k. Step number 2, we need to find C1 from the homogeneous part, which is th, 3 raised to power k. And simply from the initial value, because the initial value is t1, so it's easy to find it now. Since t1 is equal to 1, then this is equal to t 3 raised to power 0, which is equal also to 1. So substitute for k equal to 0, we substitute into this equation. We will have C1 plus 2 times 0 is 0 plus 3 over 2 is equal to 1, and from here C1 is equal to minus 1 over 3. Minus 1, 3 over 2, 1 over 2. Minus 1 over 2. So the equation we will have is that t 3k is equal to minus half plus 2k plus 3 over 2 times 3 raised to power k. Now we need to find now the last step here. Find t 3k in terms or with as Tn. Okay. So since in the beginning we assumed that n was 3 raised to power k, so k will be equal to log 3n. We will take log of base 3 both sides, because here we have 3. You can take log of other base, but you will have some extra constants. Substitute, so you will have t n is equal to minus half times 2 times log 3n plus 3 over 2 times n. How did we get this? Look at this equation. N is equal to 3 raised to power k, so it will be Tn. Now k is equal to log 3, so it will be log 3n. And 3k is equal to n, so it will be times n. And this is the last solution, or this is the closed form of the recurrence relation.